Hello, my name is Sevda and I will introduce the Connect 4 game implemented with Minimax and Monte Carlo tree search algorithm. First I will start to explain the used algorithms and then I will compare these two algorithms in terms of their success rates and execution times. I will show the demo of the game before my conclusion. Briefly, as I mentioned at the beginning, Minimax and Monte Carlo tree search algorithms are implemented to the Connect 4 game, and these two algorithms are compared based on many experiments done in different conditions. Let's start with explaining the algorithms. Minimax algorithm is a backtracking algorithm which is used in decision making and game theory. Minimax aims to find the optimal move for the computer. Two players in the game can be called as max and min. If the possible state on the board is in favor of max, positive score is given to that state. Otherwise, negative score is given. The last nodes, which is the last evaluation of the scores, is the sum of all the scores of the states. Max chooses the maximum score and min chooses minimum score. Let's look at the example of game tree, which is representing the two-player game. Unlike the Connect 4 game, there are two possible moves for the root node. Under each of the two states, it has also two possible moves. This algorithm applies depth first search, so the tree leaves two branches until it reaches the maximum depth, which is 4 in this example. When reaching the terminal node, the evaluation score is given, which evaluated using the heuristic function. Minimax highly depends on how well the heuristic function is when it makes its final decision. Therefore, one of the important points is designing a reasonable heuristic function. After we have evaluated scores, the algorithm will compare the scores and backtrack the tree until the initial state occurs. Alpha-beta pruning is an optimization technique for Minimax algorithm as it seeks to decrease number of nodes in the search tree. It reduces the computation time significantly because it removes all the nodes that are not affecting the final decision, so that searching becomes much faster. It has two extra parameters as alpha and beta. Alpha is the best value for max and beta is the best value for min so far. And the main condition which required for alpha-beta pruning is alpha is greater or equal than beta condition, because algorithm will prune the tree whenever this condition occurs. Let's examine the tree representation for alpha-beta pruning shown on the left. We can see that the tree is pruned in two nodes, E and C. I will explain the steps that are processed to remove these two nodes. The initial call starts from A. The value of alpha here is negative infinity and the value of beta is plus infinity. These values are passed down to subsequent nodes in the tree. At A, the maximizer must choose max of B and C, so A calls B first. At B, the minimizer must choose min of D and E, and hence calls D first. At D, it looks at its left child, which is a leaf node. This node returns a value of 3. Now the value of alpha at D is maximum of negative infinity and 3, which is 3. To decide whether it's worth looking at its right node or not, it checks the condition. Since beta is plus infinity and alpha is 3, this condition is false, so it continues to search. D now looks at its right child, which returns a value of 5. At D, alpha is maximum of 3 and 5, which is 5. Now the value of node D is 5. D returns a value of 5 to B. At B, beta is minimum of plus infinity and 5, which is 5. The minimizer is now guaranteed a value of 5 or lesser. B now calls E to see if it can get a lower value than 5. Now E looks at its left child, which is 6. At E, alpha is maximum of negative infinity and 6, which is 6. Beta is 5 and alpha is 6, so the condition becomes true. So it breaks the tree and E returns 6 to B. Note that how it didn't matter what the value of E's right child is. It could have been plus infinity or negative infinity. It still wouldn't matter. We never even had to look at it because the minimizer was guaranteed a value of 5 or lesser. So as soon as the maximizer solved the 6, he knew the minimizer would never come this way because he can get a 5 on the left side of B. This way we didn't have to look at that 9 and hence saved competition time. E returns a value of 6 to B. At B, beta is minimum of 5 and 6, which is 5. The value of node B is also 5. B returns 5 to A. At A, alpha is maximum of negative infinity and 5, which is 5. Now the maximizer is guaranteed a value of 5 or greater. A now calls C to see if it can get a higher value than 5. At C, alpha is 5 and beta is plus infinity. C calls F. F looks at its left child, which is 1. Here alpha is maximum of 5 and 1, which is 5, still 5. F looks at its right child, which is 2, hence the best value of this node is 2, alpha still remains 5. F returns a value of 2 to C. At C, beta is minimum of plus infinity and 2. The condition becomes true because beta is 2 and alpha is 5. So it breaks and it does not even have to compute the entire subtree of G. The intuition behind this breakoff is that at C, the minimizer was guaranteed a value of 2 or lesser, but the maximizer was already guaranteed a value of 5. If he chose B, so why would the maximizer ever choose C and get a value less than 2? Again, you can see that it didn't matter what those last two values were. We also saved a lot of competition by skipping a whole subtree. C now returns a value of 2 to A. Therefore, the best value at A is maximum of 5 and 2, which is 5. So, hence the optimal value that the maximizer can get is 5. Monte Carlo tree search and Minimax that is explained in the previous subsection has some common features in their algorithms. For instance, the game tree is similar and the logic for selecting moves is the same. However, the difference is the estimated score for each node of the game tree, because the estimation does not come from a heuristic calculation like in Minimax algorithm. In Monte Carlo tree search, games are simulated repeatedly. This is also called as rollouts, and algorithms store statistics about these rollouts in the nodes of the game tree. Monte Carlo decides the best move as using these statistics. We can say that Monte Carlo is a search algorithm that combines the classic tree search implementation alongside machine learning principles and reinforcement learning. The process of Monte Carlo tree search can be broken down into 4 distinct steps: selection, expansion, simulation, and backpropagation. The strategy behind selection uses an evaluation function to optimally select nodes with the highest estimated value. Monte Carlo tree search uses upper confidence bound formula applied to trees as the strategy in the selection process to traverse the tree. It balances the exploration and exploitation trade-off. USB formula is shown below. In expansion process, a new child node is added to the tree to that node which was optimally reached during the selection process. In simulation process, a simulation is performed by choosing moves or strategies until a result or the predefined state is achieved. Backpropagation: after determining the value of the newly added node, the remaining tree must be updated, so the backpropagation process is performed, where it backpropagates from the new node to the root node. During the process, the number of simulations stored in each node is incremented. Also, if the new node's simulation results in a win, then the number of wins is also incremented. Now in this part, I will show you the result of experiments that are carried out by running computer versus computer implementation at Connect 4 game program with various different conditions. 50 games are played for each conditions in different depth for Minimax algorithms and different number of iteration for Monte Carlo research. The winning numbers are printed on the console and statistic is calculated according to these records. Comparison is separated into as success rates and performance of computation. First experiment is carried out in Monte Carlo research and alpha beta algorithms in different depth of alpha beta, which is 1, 2 and 3. As you can see from the graph, alpha beta, which is shown with gray color, gains more success in depth 2 and more. Monte Carlo research showed achievement only against Minimax algorithm in depth 1. Second experiment is carried out in Monte Carlo research and alpha beta algorithms again, but this time I keep the depth same, but the number of iteration for simulation is different as 50, 500 and 1000. As you can see from the graph, success rates and for Monte Carlo research increases with increasing number of simulation. Monte Carlo research depends on the simulations. It may perform better with more simulations, but it changes its execution time, which I will show in the next slide. Third experiment is for comparing these two algorithms in terms of their execution time. Experiment is carried out in depth 1 and 3 for alpha beta, and I kept the number of iterations for the simulation same as 1000 because 1000 gives more success rates for Monte Carlo research algorithm. Alpha beta pruning showed faster thinking time against Monte Carlo research algorithm in 2 of the experiments, as you can see. As a conclusion for the experiments, alpha beta pruning algorithm is much more better in success rates and performance computation. It is better to prefer alpha beta algorithm instead of Minimax algorithm. We may prefer Monte Carlo research when we are lack of a good heuristic function. For the game like Connect 4 that is used for comparison is suitable for writing good heuristic evaluation score functions. So alpha beta pruning can be preferred for the games like Connect 4. Now I will show the demo of the game, which is played between Monte Carlo research and alpha beta algorithms. After doing the experiments and get results from them, I come up with these conclusions. It's better to prefer to use alpha beta pruning over bare Minimax search. We should prefer to use some form of heuristic guided search if we are able to come up with a useful heuristic. If you are lack of a good heuristic evaluation, we should prefer to use Monte Carlo research. Thanks for watching.